So let's look at the determination of potentials and E fields that are associated with dielectric materials. Imagine that you have a dielectric over this volume shown here with volume elements d tau prime. So here's d tau prime, and that's quite often written as d cubed r prime. If we take a little volume element d tau prime and locate it at a source point position r prime, we can then talk about the field due to the volume element d tau prime at the position r. So that's our field point. Associated with the position r prime is a polarization vector, capital P r prime. So that'll be located right here. The dipole that is equivalent to the polarization times the volume is equal to the dipole moment at this position, and we can consider that if d tau prime is small, then this is a constant evaluated at r prime. Well, we know that every dipole creates an electric field around it. So if we have this particular dipole, it will create a E field, and if we add them all up, we'll get the total E field. Now that E field shown here with these arrows here can exist inside and outside, and so we'll want to consider both positions. Well, if we have a single dipole, little p, we know how to find its potential surrounding that dipole. So if we define a position vector in terms of its magnitude in r hat, so that describes the field point right here, then we can also describe it in terms of the length of r and the angle theta, and that's shown here. I've got 1 over 4 pi epsilon naught over r squared, so the potential of a dipole goes as 1 over r squared, and then we have r hat dotted into the vector p. If that's a little strange, remember that we've often wrote this in this form here. So we have v of the magnitude of r and the angle theta in terms of p, and this time it's cosine theta over r squared. This r squared is this one right here, and r hat dot p is p times cosine theta. So given the polarization of the object pr prime, the potential due to p throughout the volume is given by a volume integral. So we're adding up the contributions to every little volume element. So here we have the same picture that we showed before, and here's the little volume element. So this polarization vector times d tau prime is our dipole moment at the position r prime. What's important here is the distance, the vector between the dipole and the field point. So we call that the funny r, which we did for distributions of charge. Remember what funny r is. It's the r minus r prime. The magnitude of funny r is equal to the magnitude of r minus r prime. And we can form the unit vector by just taking the ratio of the vector divided by its magnitude. And that's equal to this quantity right here. So if we take our expression for the potential and identify the r hat and the little vector p, then we can write, as we did before, that the dipole is equal to capital P d3 r prime. Put that in here, and so what we have then is this expression here that we're deriving in the following way. This quantity right here is the dipole moment at the position r prime, and so that's this quantity right here. We're dotting it, there's a dot, into the r hat, but look what we have here. This right here is r hat. So we have r hat here, we have p here, and so that'll get us to the potential if we divide by r squared. Well, 1 over r squared is shown right here. This is the magnitude of r, and that's what we have here. So 1 over r squared gives us the potential. Of course, we multiply by 1 over 4 pi epsilon naught, which is right here in the equation that we have here. So all we're doing is adding up the potential due to all these little dipoles. So we have to remember this is the volume integral over the primed coordinate r prime, see here is tau prime, over the location of the volume element d tau prime contained in the polarized material. Well, from previous torture sessions we derived this equation right here. And what it says is if we take the gradient of 1 over funny r with respect to the prime coordinates, so with respect to r prime values, that's equal to 1 over funny r squared magnitude times funny r divided by funny r magnitude. This would be funny r hat. So using that, we can take our function, the integral that we've derived so far, which is this quantity right here, and we can identify the following. We have 1 over funny r squared, which is right here. We have r minus r funny r over funny r magnitude, which is right here. And we can replace all of this with the gradient, and that's right here. Here's the gradient. So all of this gradient is equal to, let me just draw it here, like that, all of that. So we replace this dotted into p. Well, we know we can reverse the order of the dot product, so we have p dotted into this gradient. So we replace this integral with this integral. Well, using epsilon I jk notation, we proved the following, that if we take the gradient, or the gradient operator, and operate on a function times a vector, that's equal to the vector dotted into the gradient and plus f times the divergence. So if we apply this to our function up here, we have a vector dotted into a gradient, that's shown right here, and we want to replace it then with this function minus this function right here. So let's take a look at that. So we're going to replace it. So what we have here then, we identify a with p, so let me just draw that. So a is p. The function is this quantity right here. So this is a scalar function, and that's going to be what we call f. So coming down here then, if we see that we're going to use our identity, then we'll have the divergence of this vector right here, and the function f is equal to 1 over this. So this is equal to this term right here. It's equal to this term. The minus sign is associated with this here, and so our function again is 1 over funny r, and then the del dot vector, the vector is p, and so we have del dot p. So this expression here, which we've divided now into two volume integrals, is equivalent to this expression up here. So here we go. We're going to take the first one. So we're going to take the first integral in that sum, and that's equal to this expression here. Where we're headed is that we want to turn this into a surface integral. So we apply the divergence theorem. Remember, this in general is equal to this, that we have a volume element of the divergence is equal to the surface integral of the vector, where the surface encloses the volume V. So looking at our expression right here, the vector A is going to be all of this, and so we take the divergence of that, and that will be equal to the vector, so here's the whole vector right here, dotted into the surface element, which we're going to call dA prime. Now what surface are we talking about? Well, we're talking about the surface of the dielectric, and so that's going to be S prime. So now putting the two together, so we have the surface integral right here, and this is the volume integral right here. If we identify the p dot dA in terms of a normal vector to the surface, then we'll have p dot n hat dA prime, where this is the magnitude of the surface area element. And then we'll keep this right here, but I want you to notice that there's a divergence of capital P here. Okay, so the first integral is over the surface of the polarized object. The second integral is over its volume. So the potential of a polarized object can be expressed as the sum of the potential of a surface charge density and a volume charge density, where we define those densities as follows. The bound surface charge density is equal to p dot n hat. The bound volume density, so this is bound charge per unit volume, is equal to this quantity here. The minus sign comes from this minus sign right here. And n hat is the outward normal from the surface of the dielectric. So that's a very important result. These are equations for surface charge density and volume charge density due to a polarization of the dielectric. And this is the polarization as a function of position. So these represent the bound surface charge density and the volume charge density obtained before when we used just cartoons basically in parallel plate geometry. The prime in the divergence implies that it should be evaluated inside the dipole distribution, and that's given by the position vector r prime. Well, let's show that for a neutral polarized dielectric, the net polarization charge is equal to 0. So here we have a polarized object, and so we have a bunch of capital P's throughout the material. Well, this should be the case. It should be 0 because the polarization results from very small charge separations, which are all bound charges, and this includes any orientation polarization that would occur. So we agree that there's no charge, there's no free charge because it's a neutral object. So let's use our charge density equations right here. So we have polarization P dotted into the normal vector at the surface of this object, and we'll have a charge density inside, a bound charge density inside, if the polarization has a divergence. Well, here's the results. The net charge due to polarization will be the net charge on the surface plus the net charge in the bulk. So let's take the surface density, surface charge density on the surface of the dielectric and integrate it over the surface. That would be the total charge on the surface. Well, this quantity right here is equal to p dot n. So that's this equation right here. So we've just put that back into the surface integral. Integrate over the surface, and to be exact, I should put primes here and a prime here. And so that will be equal to the polarization P at r prime dotted into the ds prime vector, because that's what this is equal to. The bulk charge is found by integrating over the volume the bulk charge density, the bound charge, over the volume element, d tau prime, and so putting the expression that we have for this charge density, which is up here, minus the divergence of P, and that's shown here. So this will be the net result. So we've got two integrals here, one with a minus sign. Let's go backwards and use the divergence theorem and look at the volume element. The volume integral of del dot A dV is equal to the surface integral of A dot ds. And so we'll take the charge density, or the charge in the bulk, and represent it by a surface integral. So we're going to take this divergence right here, this divergence, and change it into a surface integral. And that's shown here. So we have P dot ds, capital P dot ds, capital S, with the minus sign because it has a minus sign right here. So if we look at these two things, here's the charge on the surface, here's the charge in the bulk, they're equal and opposite. And so if we add up the surface charge and the bulk charge, as you might expect, we have this condition here that we have one minus the other one. So we add those two together, we get 0. So if you look at this, then you have this object, and it's polarized. Then if you look at the result, you have, say, dipoles here and here. Okay, so this is a positive charge here, this is a negative charge here. On the surface you'd have all these dipoles giving you the charge density here, but if you look inside you'll also have these vectors due to the polarization of the material inside. And what this result says is that if there's no free charge here, you polarize the material, and the net result is all of the dipoles add up to 0 charge. Well, let's look at the electric field produced by a uniformly polarized sphere of radius capital R. And we'll orient the coordinate system such that the uniform capital P is equal to P0 times Z hat. So we orient the coordinate system so that it's along this Z hat direction, and that's the direction of P. So if we look at the coordinates, then here's our capital R off in any direction, that's a scalar. And we have the Z-axis here, and we have the normal vector to the sphere given by n hat. And theta would be the angle between the point that we're interested here and the Z-axis. So for P constant inside the sphere, so anywhere in here where we have a P0 Z hat, the divergence of that is equal to 0. So that means that the bound charge density is equal to 0. At the surface, we have the charge density, the surface charge density, equaling n hat dot P. And if we look at the equation for P, then the n vector dotted into P is going to be P0 n hat dotted into Z, and that's going to be P0 times the cosine of theta. You realize right here, these are unit vectors, which gives you cosine of theta. Well, we've done a similar free charge distribution problem. If you remember, if we have a surface charge density which is proportional to cosine theta, then we can derive the potential, and we found that this was proportional to the n equal 1 Legendre polynomial, which turns out to be cosine theta. So looking at the results of the potentials on the inside and outside for the charge distribution that we talked about, in general it will have a constant C1 times r cosine theta. That's for inside. Outside it'll be a cosine theta over r squared times a constant C2. And when we had the charge densities, we determined these from the boundary conditions. Well, similarly, we have to look at the appropriate boundary conditions for this polarized sphere. The first one is that the two potentials must be equal as we go across the boundary. So in other words, there's continuity in the potential. So at r equals capital R, we would have the inside potential equaling the outside. And so we've replaced little r with capital R, and we can use that to get one of the constants in terms of the other constant. And if we do the algebra, this is C1 equals C2 over R cubed. The other boundary condition is that the normal component of the E field, E sub r, at the sphere's surface satisfies the following equation. The change in the normal component of E, which is E sub r, has to be equal to the surface charge density over epsilon naught. And so we can find those quantities by taking the derivatives of the potential and putting in a minus sign. This is the R component of the gradient with a minus sign. So doing that then, this would be for outside, so we have minus the partial derivative of the potential at the outside with respect to little r, evaluated at r equal capital R. And the minus sign is this minus sign right here, so that's E outside. Then we do minus E inside, and so this minus sign and this minus sign gives us a plus sign times the derivative. So when we do that, evaluated R equal R, then we'll take that sum, or this actual difference, and set it equal to the bound charge density, surface charge density, divided by epsilon naught. And if you go up here, just to remind you, the bound charge density is P0, capital P0 times cosine theta. So we put that right here, divided by epsilon naught, and we have a relationship now between these two expressions and P0 cosine theta over epsilon naught. Notice that we have cosine theta that's common to all of these terms, so we can cancel it out. And so we're left then with this expression here, 2c2 over r cubed plus c1 is equal to P0 over epsilon naught. We've already found c1 in terms of c2, so if we put that in, then we'll have 2c2 over r cubed plus c2 over r cubed is equal to our right hand side. So we can solve for both of these now. We have c2 in terms of P0, we have c1 in terms of P0, and these are the constants that we need to define our potentials inside and out. So given that, then we can take our equations for the V inside, V out, put in the expressions we've determined, and so if we evaluate V inside, it's equal to this quantity here times Z. So it's a linear function in the Z direction. Outside, we get this expression here, so we have P0 R capital R cubed, and then times cosine theta with this down below. So using the gradient, we can find the fields, and so again the gradient of the E inside will be evaluated in the Cartesian system because we have Z dependence here. So taking that gradient, we end up with this expression here for the E inside. Now this is very important because of the spherical geometry, we end up with a expression where we have a constant times Z hat. This is a constant electric field inside of this sphere of dielectric. It's pointed, by the way, in the direction that's opposite to what you might expect. Remember, the polarization was in the positive Z hat direction. The E inside is in the opposite direction. E outside is a little more complicated because we take the V outside and take the gradient of that. So here's the gradient that we have to have, and it's two terms because we have a potential which has both R and theta dependence. So taking the del operator right here times, or dotted into, taking the gradient of this function here, where this is the del operator for the spherical coordinates, that leaves this expression right here. So you'll have to do the two differentials to see that, but I think what's incredible is that we have here a function that goes 1 over r cubed times this combination of 2 cosine theta times r hat plus sine theta, theta hat. Well, that should look familiar to you, because what we have here is potentials, which are potentials of dipoles right here. We have a constant E field in the minus z direction, and we have an E field that is outside, which is the E field of a dipole. I think you can recognize that here. And it has that dipole R dependence of 1 over r cubed. So we can relate V outside to a dipole P, which would be right at the center of the sphere, and it will look like this. We have V outside equaling this quantity here, which we've shown, and we can take the V outside and write it in the following way. So here it is again. We just multiply by the volume of the sphere divided by the volume of the sphere, so this is just 1, and then work this out, and we'll end up with k, little k, 1 over 4 pi epsilon naught times p dot r hat over r squared. And here's what the dipole is equal to. It's equal to the volume of the sphere times p0. So for a uniform sphere with p0 pointing in the z direction for the vector p, the little p that we need to get the outside E field is just equal to the volume of the sphere times p0. So it's like you take this sphere that has all these dipoles all over, and you add them all up to give you a little dipole in the center with this magnitude, and that will give you the field outside of the sphere. So what have we done? We've replaced the polarized sphere of radius capital R with an equivalent dipole, capital P times the volume of the sphere. Remember, we're using the far field potential, which is R much larger than capital R. So here's what the combined streamlines look like. So inside, remember, we had a uniform field in the opposite direction to the polarization P. Polarization is in this direction here, positive z direction. Outside, you have the field of a dipole, where the dipole, realize the direction of these fields is such that the dipole is oriented like this, in parallel or in the same direction as capital P. So this is the net combination of the description of the E field generated by a uniformly polarized sphere. So E inside is constant. Minus sign says it's in the opposite direction of the polarization. E outside is a dipole, and the dipole moment will be given by the total volume of the sphere times the magnitude of the polarization. So one more time, notice that the E field inside and P point in the opposite direction. And if you remember, that was what happened in the parallel plates. So next time we'll continue looking at some potential and E fields associated with polarized dielectrics.